Hi everyone, so this week and next week I'm just going to post one video each week. And don't forget to sign up for reviews for your portfolios and such. And to fill out your end of the semester, whatever that's called, like the surveys and stuff. Okay. So I'm going to go through a final exam this week, and then next week I'll go through another final exam. Sveta will be doing different kinds of videos, and of course hers are like synchronous, so if you want to go and ask her questions, you could do that. You can still email me, use the Piazza, all the things. Okay, so let's get through it. Answer each of the following. Give an example of an increasing sequence of real numbers that converges to the number 8. Okay, so remember sequence, maybe we have like an equals n plus 8. So that would be increasing, for example, but that's not going to converge to 8. So let's see. Often what I think about is I think about stuff that has to do with, so we want an 8 somewhere in here, right? And then probably a 1 over n. Because if we do, for example, if we do 8 plus 1 over n, the 1 over n is going to go to 0. So this does converge to 8, but actually, as n increases, it gets smaller. So if you think about it, when n equals 1, this is 9, but when n equals 2, this is 8.5, okay? So maybe what we could do instead is we could subtract 1 over n. So now it is getting bigger. So when n is 1, this is 7, and when n is 1/2, and when n is 2, then this is 7.5, so we're going up, but still converging to 8. And you probably want to say n in the natural numbers. Okay, all they needed to be was real numbers, so that's okay that we have fractions, converges to number 8. Awesome, and they're increasing. Okay, so that'll be my answer for this one. That was terrible. There we go. We could always make it a piecewise function. So f of x equals, how about, oh, yeah, okay. Square root of x, if x greater than or equal to 0, square root of x, so we get 0 to infinity on the y-axis. So we need to miss something down here. What if we did, ooh, I know, okay. What if then we did x minus 1 for x less than 0, and so we would miss like negative 1/2. Okay, good. Cool. But still injective. Okay, cool. Using the division lemma, find Q and R such that that is true. Note that, what? Oh, using the division lemma. Okay, we find these integers. Note that there is only one unique answer for this question. Right, because that's the division lemma. Okay, so let's pull up our handy dandy calculator because I'm feeling a little tired. So divided by 46. Okay, so 46 goes into 165 3 times, but notice how it's going to be negative. Well, let's see. We would be tempted to say, okay, let Q be negative 3, but then who is R going to be? Remember, R has to be, oops, sorry, we got that vice versa. It has to be less than 46, but also it has to be bigger than 0. So if we did do Q is negative 3, so let's see, so 3 times 46, oops, that's, so we would have negative 165 equals negative 138 plus R. Well, for this equation to be true, R would have to be negative, but we can't allow that. So actually, we have to go one more. So we do Q equals negative 4, okay? So 46 times 4 is 184, so negative 184 plus R. Okay, so now if we add that to the other side, what do we get? Well, we get that 19 equals R. And is that allowed? Yes, that is. Okay, so maybe let's write it nicely. So this is where that uniqueness comes from. So if R was allowed to be negative, it wouldn't be unique because we could choose Q to be -3 and then R could have been negative. But this is what gives us the uniqueness that R has to be positive. Or at least non-negative, because it could be 0. All right, assume that you know that twiddle is an equivalence relation on R except for point 0, defined as follows. Okay, find all distinct equivalence classes of twiddle. Are we still in just answers only? I think so, yeah, okay. All right, so kind of the idea here is positive times positive is positive, right? And negative times negative is positive. But positive times negative or vice versa is always going to be negative. We don't want that. So our two equivalence classes are going to be, let's say, 1 and -1. So 1 is all the x's and the reals except for 0, such that 1 twiddles x. And remember, this is the same as x twiddles 1 because we already know it's an equivalence relation. So we have symmetry. Well, who twiddles with 1? X in R minus 0, such that, or how about we could just skip all that. We could just say x greater than 0. Oh, yeah, sorry. We could just write this, so 0 to infinity. Okay, and similarly with -1, but vice versa. Okay, because only negative numbers twiddle each other and only positive numbers twiddle each other. And they do twiddle each other. Okay? All right. Consider the collection of sets b sub n going from n in the integers, such that for all n in the naturals, bn is that thing. Okay, so I'm going to rewrite bn as -n to n because that's just easier for me to look at. Okay, so consider collection. Oh, so we just need to figure out what these are. All right, so I often talk about how we want the trick of trying to do a few iterations. Okay, so here's B1, here's B2. So if we union these two together, so B1 union B2, it just ends up being B2 because B1 is a subset of B2. And for that same reason, if we intersect them, we get B1. In fact, the union is the whole real line, and the intersection is B1, or -1 to 1. Okay? Fabulous. All right, for each of the following... Oh, wait, are we in proofs now? Wait, what? Oh, okay, I see. Okay. For each of the following statements, negate the quantified statement. Oops, sorry. There we go. State whether the original statement is true. Okay. All right, for all P, there exists a P in those such that, and then we want to negate the inside of this. Oh, yes, okay. So the negation of P implies Q is equivalent to P and not Q. And that's because if P is false, then the statement is true. Okay? So the only way that an if-then statement is false is if the if part is true and the then part is false. Okay? That's what this says. All right. Very, very important. Okay, such that P prime of 0 equals 0 and P not a constant Pauli. All right, so, well, I believe the original statement is true. There exists a K in the naturals such that, okay, so first I need to negate. So for all K in the naturals, 3 is not. Okay, the original statement is false. Because k is always positive. Yeah, okay. So original statement, false. All right, negation for all x in the reals. There exists an n in the naturals, such that x is less than or equal to n. So a lot of people forget this, so the negation of a greater than is a less than or equal to, okay? You gotta have that equal to in just one of the two things, okay? All right. So let's see, there exists an x such that for all... Ooh, the original statement is false. And you could even prove that by the AP. All right. Full proof questions. Cool. Let x be an integer and y be an integer. Prove the following statement. All right. So we could just do it directly. Yeah, might as well. Let's just do it directly. All right. So first off, we want to assume the if part, because if the if part is false, then the whole thing is true, so it's fine. Assume y is equivalent to 2 mod 4. What does that mean? Well, that means that 4 divides y minus 2. Okay, remember, so we subtract the 2 on both sides. We get that. Okay, so what does that mean? That means that there exists some, I don't know, k in the integers such that y minus 2 equals 4k. What does x have to do? Oh, I see. Okay. Okay, so then we know that y equals 4k plus 2. All right? So now we want to introduce this x. So since x is an integer, we can use division lemma on it. There exists some, maybe we'll use L and R, the integers, such that x equals, and so remember, the special number that we're going to use is typically the number we're modding by, so 4. So x equals 4L plus R. Okay, such that 0 is less than or equal to R is less than 4. Okay, so R can equal 0, 1, 2, or 3. All right, so consider, remember, you can always ask your reader to consider something. Consider x times y. Well, what is this going to equal? This is going to be 4L plus R times 4K plus 2. What is that? 16KL plus 4KR plus, why am I blanking? Oh, 8, sorry. 8L plus 2R. Okay, well, what the heck are we even trying to show? Oh, well, we want to show that this is not 1 mod 4. Okay, so let's see. For right now, we can pull out a 4 out in front of all this. KL plus KR plus 2L. So if we went into mod land, this whole thing would go to 0 because we're multiplying by 4, which is one of the additive identities in mod 4. Now, what we want to show is that R2R is never equal to 1. Okay, so x, y is equivalent to 2R mod 4. If R equals 0, 2R equals 0. If R equals 1, 2R equals 2. If R equals 2, 2R equals 4. If R equals 3, 2R equals 6. Okay, so I write so big, maybe I'll just move over here maybe or something, I don't know. Okay, therefore x times y is equivalent to, what did we get? We either get 0 or 2, right? Because 0, 2, 0, 2, yeah. Mod 4 or times y is to 2 mod 4. Meaning x times y is not equivalent to 1 mod 4. That's what we were trying to show, right? Yeah. Okay. I think that's good. Awesome. So, all right, number 4, prove the following statement by contradiction or contrapositive. Okay. Suppose m and n are integers. If that is odd, then that is odd. Okay. So, maybe what I'll do is I'll remind us what contrapositive is. So if we have P implies Q, then contrapositive is not Q. Not Q implies not P. Okay, so contrapositive here, contrapositive here would mean if, so it's the same m and n are in the integers, but if m plus n even, sorry, even, then m squared minus n. So that would be the contrapositive statement, and so you would just prove that directly. I'm probably going to go by way of contradiction because that's my favorite. Proof by contradiction. Okay. Assume, so I'm going to assume the negation, and hopefully you know what a negation of an if-then is. Assume m squared minus n odd, and m plus n even. Cool. So I think where I'm going to start is I'm going to, yeah, okay. So I think I'm going to start with this even part. So then m plus n equals 2k for some k. K in the integers. Okay, cool. So then maybe I simplify it by I say now n equals 2k minus m. And now we plug it in. So we have m squared minus n equals now m squared minus 2k plus m. Okay, so this is somehow odd. Right? Yeah, okay. So this must equal 2l plus 1 for some l in the integers. Okay, now this is where things are going to get interesting. Okay, m squared plus m equals 2 times l plus k. I just added this on the other side, plus 1. Cool. All right, still odd. But, since m an integer, m odd or even. If m odd, then m squared's odd. Remember this, the m odd if and only if m squared odd. And we have the same thing for even as well. You won't have to prove that unless we ask you to, of course. But you can use it in a proof if that's not what they're asking. Okay, so if m odd, then m squared's odd. And odd plus odd equals even. Contradiction, m squared plus m odd. Okay, so then maybe m is even. Well, it's going to be the same argument. Then m squared, even, and even plus even is certainly even. Contradiction, m squared plus m. Therefore, if m squared minus n odd, then m plus. Okay. State whether the given set E is bounded or unbounded and justify your answer with a proof. Interesting. Okay. All right. So let's see. It's going to be unbounded. Okay. So how I did that quickly in my head is all that we need. So another way for us to say this is we want integers such that there exists some k in the integers as well, such that z equals 9k plus 7. And there are certainly infinite, that's certainly unbounded, because you could just make k however big you want it to be, and that would make z big. Okay, but let's prove it now. So I'm going to say unbounded, sorry. All right, and somewhere when you're writing this proof, either before you write the proof or in the proof, you want to mention what the definition of bounded is, okay? Okay, or unbounded, because they're negations of each other. Okay, I'm going to do it by way of contradiction. Assume E bounded, meaning there exists some, let's say, m in the non-negative reals such that for all elements x in E, absolute value of x is less than or equal to. Okay, and then unbound is just the negation of that. Okay, so we don't need to state both, just one of them. All right, so I'm assuming that we have this m here. Okay, but we're going to try to show that that's actually not a bound. Okay, this is when I usually move over to my scratch work here. Okay, so here we go. So we have, so what do we want? We want some x that is bigger than m. There's absolute value that's bigger than m. What does that mean? Well, that means 9k plus 7. And we can just let it be positive. That's fine. We know we can find positive things. Sometimes all you're working with is negative things. Here we're working with negative and positive. So either way that you went about it, you could solve that it's unbounded. But yeah. Okay, so we want some k that does this. So what does that mean? So what kind of k are we trying to look for? So m minus 7. So k is bigger than m minus 7 over 9. Okay. So since m minus 7 over 9 is a real number by AP, there exists, let's say, a capital N in the naturals, such that n is bigger than m minus 7 over 9. Now let's consider 9 times n plus 7. This is equivalent to 7 mod 9. Therefore, 9n plus 7 is an element in E. Okay, because remember, you always want to show why it's an element in E. Because if you just pick some random number and show that it's bigger than m, well, that doesn't matter if it's not in our set, right? We only know this for our set. Okay. All right. So now that's in there. Now let's do 9n plus 7. Or no, sorry, we can do blah, blah, blah. Oh, okay. Maybe we could say like by assumption or something. By assumption, absolute value of 9n plus 7 is less than or equal to m. Well, this is positive, so we get 9n less than or equal to m minus 7. And then n is less than or equal to m minus 7 over 9, contradiction. Therefore, so why was that a contradiction? Well, we specifically picked n to be bigger, strictly bigger than that. Don't write as sloppy as me. That would be my advice. I'm sure my teachers at school always had a pleasant time grading me. Okay, so let's see, is this... Okay, so even if it's not reflexive, you still want to show if it is these ones, okay? All right. Reflexivity. So check for all x in the naturals. Does x twiddle itself? Okay. So you might want to write these kinds of notes not only for yourself but for the grader so that they know that you know what you're talking about. Okay, so we want to check that. So let's do it. Let's check it. So, x is strictly bigger than x minus 1, so x does not twiddle itself. Okay, so no, not reflexive. Maybe I should say this. So part 2, check if x twiddles y, then y twiddles x. Okay, that's what symmetry is. Well, you want to assume the if part. So if x twiddles y, then x is less than y minus 1. Okay. So we want to see, is y less than x minus 1? Okay. Well, if we rearrange this, x plus 1 is less than y, and x plus 1 is bigger than x minus 1. So x minus 1 is less than y, meaning that x minus 1 is not greater than, not symmetric. Okay, how about transitive? Check, if x twiddles y and y twiddles z, then x twiddles z. Let's see if this one's true. Okay, so assume x twiddles y and y twiddles z. Then x is less than y minus 1 and y is less than z minus 1. Okay, well, y minus 1 is less than y, so x is less than y minus 1 is less than y is less than z minus 1, giving that x is less than z minus 1. Woohoo! Finally! So transitive. All right, so one of them, I have one of them. Oh, I should probably actually say x twiddles z. And I should probably say up here, then y does not twiddle x. Cool. All right, so state whether the given sequence is convergent or not. Yes, it is. It is convergent to 4/8, which in fact is the same as 1/2. Okay, cool. Using the definition of convergence, that is the epsilon n argument, prove the answer from part A. Okay, let's do it. Proof. So remember, we want to choose some epsilon bigger than 0, okay? And then we immediately go over into Scratcher, into our dream world. Okay, so what is it that we want? Well, we want that a sub n minus 1/2 is less than, well, let's start plugging in all this craziness. 4n to the 5th over 8n to the 5th plus 1. And often the way to go is to get common denominators and combine them. So maybe let's start with that. Let's start doing that now. Okay, so we have 8n to the 5th plus 1 over 2 times 8. We would like this to be less than epsilon. Let's see what happens. Well, first let's just work on this thing, because sometimes we have to like change the fractions and stuff. We'll see. All right, so those two cancel. Okay, cool. So we get 1 over 16n to the 5th plus 2. Okay, so recognize, since n is a natural number, we could get bigger and just start talking about 1/2. But now all of a sudden you're restricting what epsilon can be. So now epsilon has to be bigger than 1/2. We want epsilon to be able to get as small as it wants. So whenever you absolutely get rid of the natural number, the variable, that's usually a bad sign, that maybe you got too big too fast. Okay? But we can get rid of the 2. Okay. How about we just stick with this? Actually, we could even make it even simpler for ourselves. We could get rid of the 16, and we could even just make it 1 over n. Okay, we're getting too ahead of ourselves. Let's just stick with this. So we want that to be less than epsilon. Okay, so then, since we know epsilon is bigger than 0, we can divide by it. So let's divide by epsilon and multiply both sides by 16 n to the 5th. And we know that both of them are positive. Okay, so we don't have to worry about flipping signs. So maybe we look at 1 over 16 epsilon and then all to the root. Okay, so that's our capital N that we'll need to pick. Okay. By AP, choose capital N bigger than 1 over 16 epsilon to the 1/5. Okay. All right, so remember this is going to go in steps. So first we just need to show that, so we show like, why can't I think with my brain today? Okay, for n bigger than or equal to capital N, these little n's being in the naturals, we have a sub n minus 1/2 equals all this stuff. So what do we get? So we get 1 over 16 n. So you don't have to do it again. To the 5th plus 2. So this is less than or equal to 1 over 16 n to the 5th. Which now we know we're working with something positive, which is less than 1 over 16 capital N to the 5th, right? Because capital N is smaller, which we know is less than epsilon. Bada bing, bada boom. All right. Therefore, yay. Okay, cool. All right. Use induction to, oh yeah, nice, okay. To prove the following statement. Any other proof will receive at most half credit. Okay, well, that's nice of them. All right, proof. Base case. So let n equal 1, then 2 times 1 cubed plus 1 equals 3, and 3 divides 3. Check. Remember, you don't just jump into this statement because that would be you're assuming that, okay? You want to talk about what they are and show that that's the case. Inductive hypothesis. All right, assume true for some, okay? I notice a lot of students will make a little booper here and they'll say for all. If it's true for all, you're just assuming that it's done, that's all true, okay? You just want to assume for some k, for one k, okay? Now, inductive step. All right, so up here we said that 3 does divide 2k cubed plus k. All right. Now we want to show that 3 divides 2k plus 1 cubed plus k plus 1. Ah, so many parentheses. Wow, crazy. Okay. All right, so we want that. Consider just this part. So 2 times k plus 1 cubed plus k plus 1. So what is that? Oy. Well, we get k squared plus 2k plus 1 times k plus 1 plus k plus 1. That's 2k squared plus 4k plus 2. Oh, shoot. Well, that's fine. I mean, that is true, but I just did it out of the order that I wanted to do it. 2k squared, okay. And then plus k squared plus k plus 2k plus 1. 1, 2, 3, 4, 5, 6. Cool. Plus k plus 1. 2k cubed plus. So what is this? So this is 3k squared. So 6. Oops, sorry. Yeah, no, that was right. 6k squared. 3 again. So plus 6k plus 2 plus k plus 1. Woo! Plus. Oh my gosh, I made this so much harder than it needed to be. Did I? No, I didn't. No, I didn't. Never mind, I lied. Okay. 6k squared plus 7k plus 3. Okay. So what do we know something about? We know something about this friend that we have up here. Okay. So let's do something with that. Can we, for example, can we pull that out? So 2k cubed plus k. What do we have left? Well, we're going to have 6k squared plus 6k plus 3. That's all divisible by 3, so that's helpful because that's what we're trying to show. Well, okay, this thing is also divisible by 3. So maybe up here we could say then there exists an L in the integers such that 2k cubed plus k equals 3L. Okay, so this would be 3L by induction hypothesis plus 3. This equals 3 times some giant. Okay. Which is in the integers. Therefore, you might want to make a statement like since k and L are integers, then that's an integer, but that's okay. Therefore, 3 divides k, oopsie, 2k plus 1 cubed plus k plus 1. So, by induction, 3 divides 2n cubed plus n for all n in the naturals. Yay! That was our original statement, right? Or was it proving something totally irrelevant? Nope. And remember, you want to mention induction in your conclusion there. Okay, define the function, that thing, via that assignment. Okay, prove that it is injective. Okay. Challenge accepted. Okay, so remember, injective is an if-then statement for all things. Okay, so assume, T. T of P1 equals T of P2. Then what does that mean? Well, that means that x times P1 0 plus P1, maybe I should use P and Q, that might be easier. P prime 2 equals x times Q0 plus Q prime at 2. Okay, well, what the heck does that mean? I'm glad that you asked. So what we can do is we can since P and Q are both in P1, there exists, what do we need? We only need A and B. A, B, alpha, beta, maybe, in the reals, such that P of x equals AX plus B, and Q of x equals alpha x plus beta. Okay, so now let's plug and chug. So then x times b, right? Because that's when after you plug in that, and then plus, so p prime is just going to be a, so I don't even care what I plug in for that. Okay, equals x times q of 0, that's just beta, plus the prime, that's just alpha. So xb plus a equals x beta plus alpha. The only way that this can happen is that b equals beta and a equals alpha. So P equals Q. Therefore, T injective. And you might want to mention somewhere what the definition of injective is. I'll leave that to you, because I have the luxury of not actually taking a test right now. Okay, so proof. Surjective. So we want to just choose some Q in P1, the codomain, and we want P in P1 such that T of P equals Q. All right, so that's what we would like to happen. So there exists, maybe I'll stick to alpha and beta, maybe alpha and beta in the reals such that Q of X equals alpha X plus beta. Okay. But a lot of the work that we did over here can prove to be very helpful. So maybe we don't have to do scratch work. So did you notice T of Q, that polynomial, was the reverse. So it was beta X plus alpha. So it took the coefficient on X and it put it as just the coefficient, and then took the coefficient and put it as the coefficient of X. Okay, so consider beta X plus alpha. This is degree 1, which is in P1, sorry. Because we can't promise that it's degree 1 because beta could be 0, and alpha and beta could both be 0, and that's just a 0 polynomial, but that's okay, that's still in P1. Okay? Alright, so consider this. Now, take TP. Oops, sorry. That's not right. There we go. Alright, what do we get? So we get X times P of 0, well that's alpha, plus, so maybe we should even write this out some more. So P prime of X equals beta. P of 0 equals alpha. Okay. Cool. All right. So this equals alpha X plus beta, which equals Q of X. Therefore, T surjective. Yay. So that actually means that it's bijective and we could find its inverse. Congrats! Yay! Okay, excellent.